Let's play a quick game of Would You Rather. So, would you rather receive X amount of dollars a day, or would you rather have your money compound? Now let's quickly model this problem with a little graph. Although the answer seems obvious and we all know which we take, for the sake of not being ignorant, the answer is that it depends on the amount of time we're talking about. If we need the money soon, then for some time it's worth taking X amount of money a day. If we need the most money across any amount of time, well, we should take the compounding model, because clearly after a sufficient amount of time has passed, we'll have more money. Now, what do we, good computer scientists, even care about this problem that seems like a finance problem? Well, we've started the path of learning how to compare two functions to each other. We've started the path of learning asymptotic analysis. Asymptotic analysis is pretty much a fancy word for the evaluation of the runtime of an algorithm. In this kind of analysis, we derive which function dominates another, just like we did on screen visually. This kind of comparison is useful for computer science because we can model the runtime of our algorithms as functions. Back to our example. In our example, we know that we would pick G. Now, this means that we actually have an intuition as to how asymptotic analysis works. We know that after some time, it's worth it to pick a faster growing investment than it is to pick a steady but big investment. Now, this intuition we have that after some time, one function is better than another is what we'll call domination. And we're going to work to provide an actual definition for domination later in the video. But for now, we can also think of it visually as one function dominates another if that function totally encapsulates the other. So we see that G dominates F because visually it's on top of F at every point after n sub 0. Now here's a cool consequence of knowing that our function, which models our algorithm runtime, say F, is dominated by function G. If we know that our algorithm is dominated by function G, we can say that the upper bound of our algorithm runtime is G, or that the slowest that our algorithm will run is modeled by the function G, if we just exaggerate our function F. Now that we've realized through this example that we have surprisingly good intuitions for comparing functions, I'm going to teach you guys the actual standards used by computer scientists so we can formally compare functions. The first standard I'd like to touch on is that when we say algorithm runtime, what we really mean is the number of instructions executed by the algorithm. We do not mean the actual clock time it takes for the algorithm to run. This is because clock time factors in so many variables that are outside the control of the algorithm, such as processing power to name one. The next standard I'd like to talk about is heavily related to the first, and that is that we have to choose a model of computation when discussing and analyzing our runtimes. What that means in short and in simple terms is that we're going to choose the building blocks of our analysis. We're going to choose which actions take one step. For example, we're going to have comparison and equality checks take one step. Then we're going to have the basic arithmetic operations take one step. Our functions are going to be compositions of these basic building blocks. The next standard I'd like to mention is that we're only dealing with large input sizes here. And the reason for that at a high level is because we really only want to pay attention to the interesting part of the function. And we really want to see what happens in sort of the worst case and when we really expose the differences between our functions. Now we're going to get to the standard that I know you've all been waiting for, and that is the definition of the big O notation. Big O notation formalizes the intuitive idea of domination that we formed in the motivating example of this video. Now I'm going to translate that intuition into math. We say f is O of G if f is less than G for all n after n sub 0. Notice how this comes exactly from the intuition we formed at the beginning of the video, which I redrew here on the right. Let's break our intuition a bit. What if f equals x and g equals x squared over 100? We know that x squared will dominate x after some time. So how should we modify g to cancel out any such annoying coefficients? We could simply set c to 100 in this case to cancel out the 1 over 100. This is the intuition behind why we have c. C is a trick that lets us cancel out having to write coefficients in the statement f equals O of G. The mathematical reason is that we really want to compare f to the class of functions represented by g, as opposed to g specifically itself. So this is the most technical concept that we've learned so far in the video and that we're going to learn. And there's one last thing I want to say before continuing. This definition was designed to make it very easy to compare algorithms. Practically, when we compare algorithms, we really only care whether or not the algorithms are linear time or logarithmic, or whether they belong to a specific class of functions or not. We don't care about coefficients. We don't care about negligible terms. For example, if we're writing a function that is looping over a list of size n and has a return statement and has a few extra constant amount of variable assignments, we don't really care about those little variable assignments and the return. What we really care about is that loop, since that's the bulk of our algorithm and it grows with the input size. So given f equals O of g, f is dominated by g. We also have notation called big omega. So if f equals big omega of g, it dominates g. So the roles are reversed in that case. And a lot of the logic is similar. And what big omega does is that it proves a lower bound for your algorithm's runtime. How is that useful? Well, it'll tell you that this is the minimum number of operations you should be prepared to run, even in the best case. The last of the standards that I want to cover is big theta. F is big theta of g if and only if f is big omega of g and f is big O of g. Now, that may seem like a contradiction, but remember that big O of g means that f is smaller than some function in the class of functions represented by g. So, if you think about that for a second, what that means is that f necessarily has to be in the same class of functions as g, right? Because if we were to translate this, f equals O of g means that f is smaller than some multiple of g, and f equals omega of g means that f is greater than some fraction of g. So f is in between a multiple of g and a fraction of g. So it is g with another coefficient and possibly other negligible terms. That's as deep as I wanted to get for algorithm analysis. I don't want to cover techniques like exaggeration in this video, but I do want to leave you guys with one last example that applies these standards for generating a usable analysis. Let's find the maximum of a list. The algorithm works like this. We keep track of the maximum number, which by default we set to the first item in the list. Next, we loop over the list to ensure that if there is an item greater than the max, we set the max to this greater item. Notice that we do this in two operations, one comparison and one assignment. We do this n times, so our algorithm runs in 2n operations in the worst case. To be pedantic, we also have the first assignment at the top of the algorithm and then the return at the bottom. We also don't know how the for loop iteration works, beside the fact that we know it works in constant time. So in short, we can't possibly run more than 2n operations, so our upper bound is 2n. Now recall that by our definition of O, we can conveniently ignore the coefficient behind the class of functions that 2n represents. And that class of functions in this case is c times n, so our algorithm runs in O of n time. That wraps up what I believe are the most important concepts of algorithm analysis. One last thing I'd like to mention is that the entire time we've been dealing with worst case analysis. That's because the best case for all algorithms is the same, constant time. You can enforce this best case by making an if statement at the beginning of any algorithm and checking for a specific input and mapping its return to the correct output. Long story short, best case analysis is boring, so we do worst case analysis. Thanks for watching, guys, and now we can finally get to data structures and algorithms.